Hello and welcome back to this 27th lecture on bio microelectromechanical systems. Let's do a quick preview of what we did last class. So basically we were talking about different kind of fields like stress fields. We tried to understand what stress really is in terms of area vector and the force in the normal as well as tangential direction. We also discussed some basic differences between volume and surface forces, and some examples were kind of coined, like for example gravity is a big volume force, it is a body force, whereas forces related to viscosity are more predominantly on the surface, so they are surface forces. We talked or described the stress tensor, which is essentially a matrix, a 3 by 3 matrix where you have the principal stresses in the diagonal element and the non-diagonal elements of the shear stress components. We described a basic notational classification of how to represent the stress. Tau yx would mean there is a force in the x direction, and it is along an area vector pointing towards the positive y direction. That is how we call it tau yx. So it is a stress which is shear. So area vector with which this force is associated is in the y direction, and the force itself is in the x direction. So we saw that basic classification. We tried to derive the basic Newton's law for viscosity, Newton's law for viscous motion of fluids, wherein correlation was drawn out between the shear stress tau xy with the rate of deformation du by dy, and we classified different fluids as Newtonian, non-Newtonian. Newtonian wherein this stress and the velocity gradient are in direct proportion with each other, constant of proportionality being viscosity, which later on got converted into kinematic viscosity, because a better physical idea would be to compare the viscosity absolute values with the density of the solution or the medium. Okay. So then we talked about various different kind of non-Newtonian fluids like pseudoplastics, wherein the viscosity seems to go down with the deformation rate. Dilatant, where the viscosity would have a reverse behavior going up with the deformation rate, and then Bingham plastics, which would essentially behave as a solid under a certain, up to a certain yield stress, beyond which it will follow the path of a Newtonian fluid. And then we talked about thixotropic materials, essentially, where we described about properties related to the variation or the temporal variation of viscosity with time. That means the viscosity index neta would vary typically temporally with time. It will actually decrease with time. Okay. So then we were just about describing the differences between viscous and inviscid flows. Inviscid flows, again, definitionally are flows where the viscosity can be treated as 0. It is normally it's really an idealized situation. It never exists in nature, or there is no fluid in nature which exists with a viscosity of 0 value. But then in scale flows or in macroscopic flows, we can consider a region which becomes inviscid because of being away from a flat plate, and we were actually describing the situation by considering what would happen when a flow of some uniform velocity passes over a flat fixed plate. So the proximity of the plate does not anymore matter to create a velocity gradient. So those are inviscid regions of the flow. Let us go ahead and actually look at a little more of what really happens when the flow meets a flat plate. So we were talking about a flow coming in the x direction with a uniform velocity, let us say u infinity, as you can see here, and a flat plate being positioned in the OX direction, okay, as this. And then we were talking about 2 points A and A dash, which were represented as x1 and x2 on the x coordinate. So some conclusions about this process is that if the pressure does not vary in the x direction, and the velocity at B would be uniform u infinity, so we can assume that it kind of seems reasonable to say that the velocity would increase smoothly from y equal to A to y equal to B. Okay. So you have a case here where there is no gradient of pressure in the x direction here, the pressure is pretty much constant. You assume u infinity to be constant at the ab initio when it has approached the plate. Then you consider that there is almost always a zone of no slip which comes into this layer, which is close proximity of the plate, which actually goes all the way up to u infinity beyond a certain y. Okay, and let us say the point where it goes to u infinity is B. So there definitely are shear stresses in the region BC. C is the point at the surface here, and B is the point from which the velocity goes back to u infinity, and beyond this the flow behaves as if it were inviscid. Okay, that is how we interpreted in the last class. So therefore we note that the shear stresses are present in the region 0 to y B, right, in this particular region. So y equal to 0 is this plane and y equal to yb is this plane, and essentially for any y greater than yb in this particular case, as you see, the shear forces are absent because the velocity is now all uniform and is rhyming very well with the initial velocity u infinity. Okay, so there are no whatsoever shear forces in this inviscid region, and the viscous forces or the shear forces are only between the y equal to yb and y equal to 0 in this particular region here. Okay, so we will just see what happens in x2 and this particular point. So let us look at the velocity profile in x1. We see relatively slower moving fluid exerts a retarding force on the layer above it. Okay, as time progresses, the effect of this retarding force causes the distance where the velocity is u infinity to increase. Thus at x2 yb dash has to be further away than this point here, which is the point of contact c dash. Okay, so this is a kind of proportionation rule that as the flow enters this region and it is like, let us say at point C, there is a certain velocity gradient that is established between the 0 point of 0 velocity and this B, where the velocity is now u infinity. But as the flow propagates along the plate, this frictional force kind of predominates. Okay, so therefore this region here where the velocity would go back to u infinity should definitely increase, because there is energy loss in forms of friction as you move from point C to C dash. Okay, C dash of course is this new point here, as you can see from this arrow. So if we assume this to happen, then we can think that the fluid is applying a retarding force to the plate. So the force goes on increasing as it goes along from 0 towards x2. Okay, so therefore definitely the yb dash here, which is essentially this distance, should be greater than yb, because it takes a while, because the retarding force is more at b dash. Okay, I mean c dash b dash plane, this plane, and so therefore the fully developed flow here up till y, which is yb dash, should certainly be greater than the value yb. Okay, so we can also kind of reasonably assume that yc dash, so yc and yc dash are pretty much same, as you can see here, and the reason being that the no slip zone would always be kind of close to the surface. It does not go beyond into the bulk. Okay, so from our qualitative picture, we can see that we can visualize these two different flows by a separating layer between them. One where there is a shear which is existing at the bottom, starting from the plate all the way up to where the fully developed flow has happened, that is u infinity. Another which is the inviscid region, where it starts from the u infinity, I mean the fully developed flow, and goes into the bulk. Okay, so the layer which is separating these two is also known as what we call the laminar boundary layer. Okay, it is called the laminar boundary layer. So essentially, if we consider the y component of the velocity now, there is a very interesting thing which comes out, that let us say we consider the streamlines, okay, of the flow. And as we know from earlier definition, what are the streamlines? They are tangential vectors or line joining the tangential vectors to the direction of flow of particles. Okay. So, that is how streamlines can be categorized. So, let us consider the streamlines of flow in these two different flow regions. Okay. Flow region 1 here, which is the inviscid region, and flow different 2 here, which is the viscous domain. And so, what would we need to assume to maintain consistency? So, our first inclination would be to draw these streamlines kind of parallel to the plate, assuming that the fluids go past the plate parallelly. Now, interestingly, if there are parallel streamlines generated parallel to the surface of the plates, and we are saying that in one case there is a lesser amount of velocity which increases all the way to u infinity, in another case there is all u infinity, there will not be much problem in the region 1 or the inviscid region, but in region 2 definitely there is going to be mass transfer in the y direction, right, because of principally the amount of feed of a fluid. If we want the continuity to be valid, or if we want to assume the fluid as a large continuum, there cannot be any gaps in between. It can be one indivisible mass of substance flowing over the plate. So, in that case, if there is a velocity gradient and there is a tendency of the lower layers parallel to the plate to reach at a slower rate a certain point, the upper layers would move at a higher rate and try to preoccupy that point. Okay. So, there is going to be a mass transfer in order to balance such a system of flow. Okay. And this situation does not really exist, because as we know that there can be a velocity gradient, but there cannot be any really any velocity in the y direction, or there can, even if there are velocities in the y direction, this continuum failure never happens within the fluid. Okay. And so what is needed to maintain the no mass flow kind of situation? That the spacing between the streamlines, different streamlines, go on increasing their distance from the surface, the flat surface, as the flow goes along. Okay. So, the streamlines are all kind of merging out from the point where the flow has just entered along. As the flow goes along the surface, the streamlines get separated by greater and greater distances. Okay. So, they are not really parallelly oriented, they have different directions which go on spreading up more and more as the flow goes along the direction of the plate. So, essentially we conclude that the edge of the boundary layer is not a streamline, and just because of so a streamline is something across which there cannot be typically any mass transport. Okay, because tangential to the direction of the streamline, the particles are all moving, their velocity vectors are in the tangential direction to the streamline. So, there is no inward radial flow from one streamline to another. Okay. And so, the boundary layer which is the separation layer between the inviscid flow which is on the top and the viscous flow which is on the bottom is really is not a streamline, because there has to be kind of mass flow to maintain the balance between the lower velocities and the fully developed flow velocity u infinity across this layer. So, consequently we conclude that the edge of the boundary layer is not streamlined, and there is a flow into the boundary layer assuming the differences in the velocity across it. Okay. So, based on some of these concepts, we can divide all the viscous flow regimes into laminar and turbulent. Okay. In laminar regime, the flow structure is characterized by laminae or layers, and this is the regime where most microflows are kind of packed up. And the flow structure in turbulent regime, which is mostly the macro scale version of flow is by random 3-dimensional motion of fluid particles. Okay. We can also categorize, so we have already classified fluids as viscous and inviscid. We have categorized fluids into laminar and turbulent. We can also categorize fluids into compressible and incompressible, and essentially the main difference is that in compressible flows there are variations of density along the fluid medium, whereas in incompressible flow we assume the density to be just a constant across the whole continuum of the fluids. Okay. So, the flows in which variations of density are negligible are called incompressible, and there where the variations in density are substantial, they are called compressible flows. Okay. That is how you divide flows into compressible and incompressible, apart from laminar and turbulent and viscous and inviscid flows. So, let us now try to go ahead and derive the first equation of conservation of mass, or what we call the first Navier-Stokes equation. Okay. So, for that we need to assume again a small control volume. Let us say we are trying to see the amount of mass flow into this control volume and the amount of mass flow outside this control volume, and it is centered around a point O. Okay. And this is further like a cube around this point O with dimensions dx, a rectangle around this point flow around this point O with dimensions dx, dy and dz in the x, y and z directions. And what we would be looking at, that if we assume that there is no creation of mass within this control volume, so whatever is inflowing into the mass is exactly the control volume is exactly equal to the mass that is outflowing of the control volume. So, this is also known as the continuity equation or the conservation of mass equation, and let us try to mathematically or geometrically derive this particular equation. So, let us say we have an xyz direction here. This is a rectangular coordinate system, and we assume a control volume of a rectangular shape, a cuboidal shape with values dx, dy and dz dimensions. Okay. Or we further assume this point O around which this control volume is equally spaced or symmetrically spaced, and we have 3 components of velocity u, v and w. It is a 3-dimensional flow. This is the origin 0 0 0, and we are trying to investigate what happens in this point O. Okay. So, the very first thing that we would like to investigate is, let us say, the density. Given we have a density rho here at point O, what would be the density at, let us say, rho x plus dx by 2, which is this particular face here. Okay. So, this can be expressed again as kind of Taylor approximation as rho plus dp or d rho by dx times of dx by 2 plus d rho by dx d2 rho by dx2 times of 1 by 2 factorial dx by 2 square, so on so forth. Okay. So, if we assume these dx to be infinitesimally small element and neglect all the higher order terms here, the rho x plus dx by 2 really comes out to be, and why we are taking dx by 2 is because we assume this whole length to be dx. Okay. And this at the center. So, therefore, this face, this shaded face here is at a distance of exactly dx by 2 from O, and that is why the dx by 2 term. So, therefore, rho at dx x plus dx by 2 is nothing but rho plus del rho by del x times of dx by 2. Okay. Similarly, u at x plus dx by 2 is essentially equal to u plus del u by del x times of dx by 2, right, where rho u del rho by del x and del u by del x are all evaluated at O. You have to keep this in mind, because we are essentially evaluating what is happening at one of the edges based on the properties of the point O, and all these values, that means including the change of density with respect to x, the change of velocity with respect to x, the velocity and the density must necessarily be at the point O. So, therefore, we can write similar equations for the other face, that is the face on this negative side, okay, this particular face, and here we can say rho at x minus dx by 2 essentially equal to rho minus d rho by dx times of dx by 2, and u at x minus dx by 2 is essentially u minus del u by del x times of dx by 2. Okay. Now, for conservation of mass, we in say, let us say in the one direction or the one dimension, we have to necessarily assume that the net rate of mass flux out through the control surface is essentially equal to the net rate of mass flux coming in the control surface. So, this is an assumption or a supposition that we have to necessarily make here. Okay. And so, therefore, we have to really see that there are not only these x faces, but also y faces and z faces, and also faces along the minus y and minus z direction. And so, the whole equation can be thought of as a problem where all these different faces have inflows and outflows, and we are trying to see how the fluid mass is conserved in this particular case. Okay. So, what we do here is that let us say let us evaluate the rates of mass flow, inflow and outflow at all the different phases. Yeah. So, rate of mass flow through the positive x phase is the one to begin with, okay, of the control volume. So, we know the density times of velocity is times of area is really the mass per second. Okay. So, density times of velocity times the area of the phase is mass flow per second. So, here in this case we can write the density at x plus dx by 2 times of the velocity at x plus dx by 2 more simplified manner as rho plus del rho by del x times of dx by 2 times of u plus del u by del x times of dx by 2. Okay. And this, if multiplied to the face, the interfacial area, okay, which in this case, as you see in case of x, is nothing but dy times of dz. Okay. So, this is the area vector of this particular face. So, you multiply this with the area dy dz in order to get the mass flow rate dy dz. So, if you solve this particular equation, you have the resolved value as rho u plus dx by 2 times of rho del u by del x plus u times of del rho by del x times of dx by 2, of course, plus you have a component here with all the dels, okay, del p by del x, del rho by del x times of del u by del x with the square of dx by 2. Now, we assume that the component dx being very small into dy dz, the area, the component dx by 2 very small, this actually can be approximated as 0, which eliminates altogether this particular term here. Okay. And so, we are left with the equation rho u plus dx by 2 times of rho du by dx plus u del rho by del x times of dy dz, and this is nothing but del rho u by del x. Okay. This is basically it just comes from the differentiation of a product formula. Okay. So, that is what the mass flow rate is really towards the positive x phase. Now, let us see what this rate would be at the negative x phase, and the only difference in this case would be that the rho and the u both are evaluated at the x minus dx by 2 phase. The area vector almost remains same in magnitude dy by dx, and so this would typically and of course, you have to have okay. So, the area vector is although it is same in magnitude, but it is actually negative in direction, it is in the exactly opposite direction, it points to minus x side in this case. So, you have to have a minus sign representing the direction of the area vector dy dz. Okay. So, in this case the expression can be simplified as minus rho u plus 1 by 2 times of again del u rho by del x, okay, whole multiplied by dy dz. From these two terms I can further simplify, let us say, this equation as well as this equation, and write it down as rho u dy dz plus half del u rho by del x times of dx dy dz, and similarly here we write as minus rho u dy dz plus half. So, there has to be a dx term here, I am sorry. So, half del up by del x times of del x del y del z. Okay. So, that is how the rate at negative x phase is. Let us do the same for the positive as well as the negative y phase. So, for the bottom pointing towards the negative y direction, we can represent this as rho at y minus dy by 2 times of u at y minus dy by 2 times of, in this case if you look at the area vector in the negative y direction, it is dx times of dz. Okay. So, therefore, this can be represented as rho at y minus dy by 2 times of u at y minus dy by 2 times of dx dz, and this comes out to be again further simplified in a simplified manner, comes out to be minus rho v dx dz plus half times of del by del y of u rho or v rho really times of dx dy dz. Okay. So, for the top surface pointing towards the plus y direction, this would come out to be rho y plus dy by 2 times of u y plus dy by 2 times of dx dz, and this if simplified would come out to be rho v dx dz plus half in the differential of with respect to y of rho v of v rho times of dx dy dz. Okay. Similarly, we do the same for the face pointing towards the minus z direction, and here we can write the velocity vector to be rho at z minus dz by 2 times of u at z minus dz by 2 times of, because this is the z direction, again the area which would be representing this is dx times of dy. Dy is this and dx is this direction. So, it is this interface that is actually being represented here. Okay. So, let us write that down as dx dy here, and so therefore, we can represent this in a more simplified manner as rho w dy dx plus half times of d by dy d by dz times of rho w times of dx dy dz, and similarly for the top pointing towards the plus z direction, we have rho, and this is a minus sign mind you, we have rho z plus dz by 2 times of u at z plus dz by 2 times of dx dy, which is actually equal to minus which is actually equal to rho w dy dx plus half times of del of rho w by del z times of dx dy dz. So, essentially the net mass flux then, as I already talked about, should be equal to the flow through plus x direction plus the flow through minus x face plus the flow through the top plus y plus flow through minus y plus flow through plus z plus flow through minus z direction, right. And we also assume here that if there were so make it very generic in nature. First of all, let us find out what is the summation of all these different flows. Okay. So, that comes out to be equal to minus rho u, and I am just borrowing these from the earlier expressions that we have derived, minus rho u dy dz plus half of del rho u by del x times of dx dy dz plus rho u times of dy dz plus half of del rho u by del x times of del x or dx dy dz, plus we have similar terms for for the y plus y minus y and plus z minus z directions. Let us write them down. So, for the y direction you will have minus let us just erase this particular illustration here, give me a minute. Okay. So, for the minus y direction we have minus rho v dx dz plus half of del rho v by del y times of del x del y del z plus rho v dx dz plus half of del rho v by del y times of dx dy dz, and similarly for the z direction you have rho w dx dy plus half del rho w by del z times of dx dy dz plus rho w dx dy plus half of del rho w by del z times of dx dy dz. So, interestingly, these first terms actually cancel each other as regards the plus x minus x, plus y minus y, and plus z minus z direction, and what you are left with are these second terms here, right here, which if we kind of sum up together, we would be getting an equation which is equal to del rho u by del x plus del rho v by del y plus del rho w by del z, and del x del y del z as the control volume with respect to this. Okay. So, essentially this is really the net rate of mass flux out through the control volume surface. So, I can write this as the net rate of mass flux out through the control surface. Now, what is interesting here to point out is that if the rate of change of mass inside the control volume is a function of is a function of time, that means there is some mass which is generated or created inside the control volume. In that case, we can always write down that the rate of change of mass inside the control volume CV is equal to del rho by del T, that means the rate of change of density, and this can be a case for compressible flows where there is a rate of change of density with time. For incompressible flows, of course, this dP by dt does not make any sense, d rho by dt, because it is 0. Okay. We assume that the density is constant temporally, there is no variation of density with time. Times of the control volume del x del y del z. Okay. So, in a more generic manner, the equations 1 and 2 here which have been derived, if added together, should give you a situation whether it is for compressible or incompressible flows. And what you can do is that the total amount of mass in this manner which either inflows and outflows or gets generated should be equated to 0 because of the conservation of mass. I mean, mass cannot be created or destroyed if you are assuming continuum assumptions inside such a control volume of particular fluid. So, in that case, the del rho u by del x plus del rho u by rho v by del y here plus del rho w by del z plus del rho by del t whole brackets the control volume dy dx dy dz should be equal to 0, and which actually can be in a more abridged manner written down as the grad of so the grad vector dot rho v vector, okay, plus del rho by del t is equal to 0. So, this is what the first of the Navier-Stokes equations are about continuity or conservation of mass. Okay. So, typically for an incompressible flow though, what we would be left with is just this part of the term. Okay. So, what we will be left with is just del dot or the grad vector dot rho v vector. So, incompressible flow cases when particularly del rho by del t is equal to 0, the continuity equation really reduces to del dot rho v vector equal to 0. Okay. So, that means the del rho u or del u by del v or Lx x plus del v by del y plus del W by del Z, with the rho taken common out of all this. Remember, in incompressible flows, this rho does not vary with time or space. Okay. So, there is absolutely no variation in the density. The density either in time or in space both remains same and constant. So, this is a situation of incompressible flows. And so, therefore, this becomes equal to 0. In other words, del u del x plus del v del y plus del w del z is 0 is the new form of the continuity equation, particularly for incompressible flows. Okay. So, let us kind of try to understand this through an example. Let us say we have given there exists a 2-dimensional flow in xy plane, for which u becomes equal to Ax. Okay. And so, you have to find the possible y component for steady flows, steady incompressible flows, using the continuity equation. Okay. And also how many y components, how many such y components would be possible. So, as we know here, del rho by del t is 0, or rho is a constant. Okay. And therefore, the whole continuity equation just changes to del cross v vector equals 0, del u by del x plus del u by del x plus give me a minute here. Plus del v by del y plus del w by del z equal to 0. Okay. So, essentially this means that, and also we already know that the flow is 2-dimensional. Okay. So, for such a 2-dimensional flow, v essentially should be a function of x y, right. The velocity v vector should only be a function of x and y. So, therefore, there is no third component which exists, or w equal to 0 in any case. So, for the compressible equation, or the continuity equation changes to du by dx equal to minus del v by del y, and let us say these all are equal to a constant minus a. Okay. So, therefore, we can safely kind of try to integrate and find out the value for the velocity v. So, as you do that, we can get v is essentially integral a dy with a minus sign plus some constant, and since we are only this v is never varying in the x direction, we can assume a function of x to be constant along the y direction. So, f the v essentially becomes minus a y plus function of x. So, this is essentially invariable in the y direction. It is a pure function of x, and so therefore, it may be treated as a constant in this particular case. It could also be a normal constant apart from that. So, essentially a possible y component for the steady incompressible flow can be expressed as minus a y plus function of x. Okay. So, you can also say that because there is a function of x involved, there are many such solutions of the y component of velocity that is possible using the continuity equation. So, let us also do a little bit of different kind of example related to an operating piston and a certain cylinder pressure to understand the continuity equation a little better. So, in this particular example, as you see that there is a gas filled numeric strut in an automobile suspension system, okay, and it behaves like a piston cylinder apparatus. The boundary conditions that are given is that at one end or at one instance when the piston is at say the total length L equal to 0.15 meters away from the closed end, okay, of the cylinder, the glass density is uniform at rho is equal to 18 kgs per meter cube, and the piston begins to move away from the closed end at velocity equal to roughly about 12 meters per second, and the gas motion in one dimensional is really one dimensional in this case and proportional to the distance from the closed end. Okay. So, it varies linearly from 0 to velocity v, which means that at two ends, at the closed end when the piston is present the velocity is 0, and when it goes to the length L equal to 0.15 meter, which is at one end, okay, from that means this is away from the closed end, farther is the farthest extremity. At that the velocity u becomes v. Okay. So, we have to evaluate the rate of change of the gas density at this particular instance, particularly when the piston is at 0.15 meters from the closed end, and we also need to obtain an expression for the average density as a function of time. Okay. So, we need to find what rho average is in terms of rho t here. So, let us actually try to solve this using continuity equation. We have a cylinder here in the example, 3 fixed ends and a movable piston, let us say here, and essentially what has been indicated here is that the gas density within this volume is 18 kg per meter cube, and this is the closed end, and this is the farthest extremity that the piston can travel, and here in the question this extremity has been given as 0.15 meters. Okay. So, essentially distance here is 0.15 meters. So, we also further know that the velocity is 0. Let us say we are talking about the x direction starting from 0 here all the way up to L. So, velocity is 0 when x is equal to 0, and the velocity really is v when x equal to this L value. And so, therefore, and also we further know that as it is given here that the gas motion is one dimensional and proportional to the distance from the closed end. It varies linearly from 0 to ux, because it is a linear variation. We can assume that the u is really equal to some constant k times of x. V becomes equal to KL because u is v as x is L essentially, or k becomes v by L, and so u essentially is again Vx by L. Okay. That is how u is. So, x equal to 0, u is 0, at x equal to L, u is equal to v. So, all said and done, this is what the velocity equation is in terms of x. So, we will now apply the continuity equation here. We know that by the continuity equation we have del dot rho v vector, okay. V is the velocity vector, is essentially and plus del rho by del t is essentially equal to 0. Okay. So, del rho u by del x plus del rho v by del y plus del rho w by del z plus del rho by del t is equal to 0. Okay. And essentially if we just put the value of u equal to ux, this Vx by L value, and with respect to this is the only velocity, mind you this is only a one dimensional case as has been indicated. Okay. This piston cylinder arrangement, and so therefore d v by d0 dv by dy really or dw by dz are both zeros. And so the only other value which comes out of this whole del cross rho v is essentially rho del u by del x, okay, or del rho u by del x. All right. And so we know that, from, because it's actually a compressible flow in this particular illustration, we have this plus del t is essentially equal to 0. So if we try to figure out what this value would be, del rho by del t becomes equal to minus rho del u by del x minus u del rho by del x. Okay. And as we know that du by dx or dou u by dou x is essentially a constant v by L, and therefore we have also the value del p by del t from equation 2 here becomes equal to minus rho times of v by L. So this minus rho v by L minus u del rho by del x. Now if you look at this is, let us say this is equation 3. So if you really look at the question of the problem statement, rho has been assumed to be uniform in the volume, okay, not with time t. Here the rho is varying with time t, it is temporally varying, but it is not varying spatially really. So therefore del rho by del x, because it is uniform within the volume, is supposedly equal to 0, and we are left with no other choice but del rho by del t on one side equal to minus rho v by L, and that is equation 4. So let us try to figure out what an integration of this quantity would result in, and what would really be the density function in terms of the velocity, length, etc. So here we would like to illustrate that the length L really is we can assume this to be equal to let us say the initial length L0 that the piston is at plus v times of t, where v is the velocity of the piston and t is the time of movement. Okay. So there is some L0 value, let us say the piston is somewhere, if you see in this particular figure here, the piston is at some value when, let us say, it moves at a certain velocity v, this value is maybe L0, and we want to consider any length L which is equal to L0 plus v times t. After time t it would be here, and this is really the new length L. Okay. So that is how we define this this whole length of traverse of the piston inside this cylinder. So if we assume this to be the final length at time t, assuming this to be the length in ab initio when the process started, we have integral d rho by rho where rho varies from, let us say, some quantity rho 0 to some value of density rho t, equals integral minus 0 to t v by L dt. Okay. And essentially, as you know that this L actually comes from this L 0 plus V t. So, we will have this as 0 to t thing of 0 to t v by L 0 plus V t dt. Okay. And so, therefore, ln rho by rho naught really becomes equal to ln L naught by L naught plus V t. If you just solve this integral, it is essentially and put the limits 0 and t, it comes out to be L naught by L 0 plus V t. Or in other words, density as a function of time really is equal to the density at time t equal to 0 plus 1 by 1 plus V t by L 0. Okay. So, at time t equal to 0, therefore, as the second part of the question assumes, del rho by del t, the change of density, rate of change of density would be rho 0 V by L, and rho 0 being already given equal to 18 kg per meter cube, when this is at length L 0 0.15 meter. This particular length, and it is moving with the velocity 12, the whole density variation with respect to time becomes equal to minus 1440 kg per meter cube second. So, as you found out here that the continuity equation can be very easily used for this kind of compressible flow problems as well, where density varies with time, as well as the earlier problem as you saw was that of incompressible flows. So, in micro scale though, if you consider the flow mechanics, mostly flows are treated to be incompressible and strictly laminar in nature, because although there are twin phase flow problems at the micro scale, but the modeling becomes extremely complicated and difficult, and so we will be limiting ourselves mostly to the single phase flow problem in such a situation. So, this kind of brings us to an end of this particular lecture. We will try to cover up the second Navier-Stokes equation, that is the conservation of momentum, in the next class. Thank you.